Hello, students. So, related to the presentation slash talk that we're going to have with Nelly Villamizar in a few days, and as some of you have commented that in the video where she introduces the topic of her work, which she's going to talk about, which is basically algebraic geometry applied to computer graphics, there are some ideas, some concepts you had difficulty understanding. I am basically going to clarify one of those concepts, that of partial differential equations. Now, I have a very limited understanding of the topic myself, so take everything I say with a pinch of salt. But I think we can make a simple, generic explanation of what these things are. So let's get to it. The first thing we could do is break up this entity into its constituent parts. So if we want to know what a partial differential equation is, it's probably a good strategy to start clarifying what an equation is, which most of you will know. I would say all of you will probably know this. We could continue with explaining what a differential equation is after this. And we can conclude with adding the last element, partial differential equation. So from bottom to top, as I said, the explanation is going to be pretty simple, so it shouldn't require much mathematical knowledge beyond what you might remember from high school. But I would say that if you are aware of what functions, and especially what derivatives are, that will come in handy. But otherwise, I'll try to at least give you a general idea. Okay, let's start with equations. So equations are pretty simple. You've encountered them in your high school or even secondary school years. And they are the constituents of, basic arithmetic and algebra. So equation, from Latin aequalis, the same thing. So equations basically say that this thing is basically equal to this some other thing. And you have the equal sign that unifies them. It has an interesting history, the equal sign. It's two parallel lines, actually. And it was a sign developed in the Renaissance with the idea that two parallel lines are the same, except that they are located at a certain distance from each other. Anyway, equal we're not going to talk about this would be a side note, but the concept of equality is a pretty complex one in mathematics. In fact, there are many different types of equalities in mathematics. Like you have homomorphisms, you have endomorphisms, you have congruences. But anyway, here we're talking about the everyday equality that we understand. So equality appears, for example, when you start seeing operations. So the typical one, operations with numbers, you have the number 2 and you have the number 3. You do the operation addition, 2 plus 3, and this gives you something that is exactly the same as the number 5. So 2 plus 3 equals 5. This is an example of a basic equation. A little bit more complicated are algebraic equations, which you study when you're a bit older, maybe like 10, 9, 10, I'm not sure. I would have to check the curriculum. And here you generally have one unknown, an algebraic unknown, an x. And you have to do some manipulations to discover what value the x might have. And here you have a few. 2x plus 6 equals 16, 3x minus 5 equals minus 1, 6x equals 3, x squared equals 2, x squared equals minus 1. Now here we start getting some complications in that the numbers that might be the solutions to these equations might not always be the same type of numbers as those that appear in the equations themselves. So for example, in 2x plus 6 equals 16, the solution x equals 5 is the solution that satisfies this equality, and 5 is a normal number. It's a natural number like 2 and 6 and 16. But in the next two equations, 3x minus 5 equals minus 1, 6x equals 3, the solution is no longer a natural number. It's a fraction, a rational number. So in the first case, it's 4/3, and in the second case, it's 1/2. So if you were to say, do any of these two equations have solutions there are natural numbers? The answer is no. But if you use another number system, the fractions, yeah, they do have solutions. And the same thing happens with the ones at the bottom. X squared equals 2. In this case, there is no natural number, there is no rational number that can satisfy this equation. The solution would be the square root of 2. That is the number that when squared is equal to 2, but no natural or rational number is of this type. The number that satisfies this is square root of 2, which is approximately 1.41, no, 1.41 in a lot of infinitely and never recurring decimals. And the same thing with x squared equals minus 1. The solution here would be the square root of minus 1, which is the first of the complex numbers, I, which is not a real number, it is not a rational number, and it's not a real number. So let's continue talking a little bit more about equations, and we could say that equations in one variable are relatively easy to deal with, yeah? Especially when their degree, that is the power to which the unknown is raised, is a small power. So most of you know or will remember how to solve like equations to linear equations where the x is to the first power, like 3x plus 1 equals 5. Those are easy equations to solve. Even quadratic ones, like x squared plus 3x plus 5, those are also easy to solve because there's a formula. And if you apply the formula, you get the solutions of the equation. Sometimes one of the things that's typically done is put all the elements of the equality of the equation on one side or the other. So you have an algebraic expression that is equal to 0. And when you do that, the x values that solve the equation are generally called the roots or the zeros of the algebraic expression of the polynomial, because they're the ones that make the expression equal to 0. And so when we're talking about one variable only, there's just an x. There are formulas that make it relatively easy to calculate this for powers up to 4. When you reach 5 or more, there are no longer easy formulas, but there are still methods for solving these equations. Problem is, you can have equations with more than one variable, like equations with 2, 3, 4, infinitely many variables. And these will be much, much, much more difficult to solve, like x squared plus y squared equals 1, or taking this as a general model, what about x squared plus y squared equals z squared? That is, which numbers satisfy the rule that the sum of two squares is equal to a third number that is also a square? Or y squared equals x cubed minus x plus 1. This is a third degree equation because the highest degree is 3, so it's a cubic. And some of these, so for example, the second one is the Pythagorean triplets. Yeah, no, it's the equation that is used and that solves Pythagoras' theorem, like if you have a right angle triangle, the sum of the squares of the small sides is equivalent to the square of the long side, the hypotenuse. And you have an infinite number of triplets that satisfy this equation. The easiest ones, x equals 3, y equals 4, z equals 5. But there are infinitely many of these solutions. For x squared plus y squared equals 1, here I can think of a few solutions, like, but not that many. If you want the solutions to be integers, so for example, x equals 0, y equals 1 or minus 1, and vice versa, x equals 1 or minus 1, y equals 0 satisfies the equation. The third one, y squared equals x cubed minus x plus 1, is what we call an elliptic curve. And they already start to become too complicated for humans. Most elliptic curves are just too difficult to do anything profitable about them or to know any substantial thing about their solutions. Sometimes these cubic, the cubic equations of this type can have, I don't know, infinitely many solutions, or finitely many, or it depends on the type also. If you want rational solutions or integer solutions, it varies. But we're getting a bit lost. So these equations, they can take physical form. Apart from being a series of numbers and letters, if you map them to the Cartesian plane, and you take the Cartesian plane with two big axes, the x and the y axis that meet at the point 0, 0, you can map these algebraic equations into here, and you get geometric shapes, and sometimes you get something that is interesting for knowing more about the equations. So linear equations, that is those of the form of powers of 1 for the unknown for the x. When you map them into the Cartesian plane, they are lines. Some of the quadratics, that is of the second degree, the second power unknown, take the form of the conic sections like circles, ellipses, parabolas, hyperbolas. The one on the bottom left is an elliptic curve, and the one on the right is a fifth degree equation, which as you can see, makes for a nice roller coaster because it crosses the x-axis 5 times, as would be expected from a fifth degree equation. So now that we have a clear idea of what an equation is, we can move on to what a differential equation is. And you have some examples there on the left, although the nomenclature might be meaningless to you, and it's almost meaningless to me as well. So in the equations we've seen until now, we had equations where the solution was a number or a series of numbers. Sometimes it's one number, sometimes it's more than one, sometimes you have infinite numbers that satisfy the equation, sometimes you have none. So the question is, what happens when the unknown in an equation is not a number? What happens when the unknown is a function? So, two things first. So, okay, what is a function first? Manolo, tell me what a function is. So the technical definition would be something like the one that appears there. A function is a binary relation between two sets that maps each element of the first set with exactly one element of the second set. To put it in more understandable terms, you can use the image on the right as a guide. So we could say that a function is a bit like a machine, where you can feed inputs and you get outputs. So for every input, which could be a number, you get one output, and only one for each input. So the algebraic equations we saw before are examples of functions. So for example, x squared. So the function f of x, with the rule for getting results being x squared, means you take let's say, for example, natural numbers, 0, 1, 2, 3, 4, 5. You put them in the machine, and the machine spits out the square of that number. So if you put in 0, you get 0. If you put in 1, you get 1. If you put in 2, you get 4. If you put in 3, you get 9, and so on and so forth. And that's a function, basically. And as with numbers, there are many things you can do with functions. That is, you can add, subtract, multiply, divide functions. So imagine if one of your functions, f of x, let's say is x squared, and g of x is, say, x plus 1, you can add them together, and f of x plus g of x would be x squared plus x plus 1. You could, for example, compose them, which means basically doing one, and with the output of that one, doing the other. So for example, f of g of x would be, let's say, take all the natural numbers and do g of x to them. G of x, remember, is x plus 1. So I take 0, the output is 1. I take 1, the output is 2. I take 2, the output is 3. And so on, forever. All the outputs of this function would be all the natural numbers except 0. And now I can plug them into a second machine, which is f of x, and we square them. So the output would be 1 squared 1, 2 squared 4, 3 squared 9, and so on and so forth. Another thing that you can do with functions is taking their derivatives. And this is important for differential equations. So the next obvious step is to explain what a derivative is. Now, those of you that have studied mathematics until the last years of high school will have a clear notion perhaps of what a derivative is. If you don't, this is too complicated to summarize easily. Let me just say that so a derivative is basically a function that is derived from another function. Like I give you a function, you can calculate its derivative, which is going to be another function that is connected to the first. And why is it connected to the first? Well, it gives us information about the first. And basically, the most important information it gives us is the rate of change of the original function. It basically tells how fast the values of the original function are changing from point to point. And there are pretty mechanical formulas for calculating the derivatives of a function, and you can take the derivative of a function more than once, so you can get the second derivative of the function, the third derivative, and so on until you go down to 0. So just to give you an example, if your original function were to be, let's say, x cubed divided by 3 plus 20, the derivative of this function would be x squared. And you can take the second derivative, the derivative of x squared would be 2x, and you can take the third derivative, the derivative of 2x would be 2. And you can even take another derivative, but the derivative of a constant is 0 always, and then there's nothing else you can continue doing. The game reaches its end. So back to differential equations. What is a differential equation? We said that it's an equation like the other ones, but instead of having numbers as its unknowns, it has functions and its derivatives as unknowns. So for example, the one on the left, which is written in 3 different ways, but it's the same, it's a question of notation. The one on the left is saying which function, so not which number, which function y or which functions y satisfy the equality, satisfy the equation that if you multiply the function by 3, you get the same result as multiplying the second derivative of the function by 2 and adding multiplying the first derivative of the function by 2 and adding the second derivative of the function. So in this case, if you know any mathematics, there are probably infinitely many solutions. An easy one is e to the x, which is the only function whose derivative is equal to itself. So the derivative of e to the x is e to the x. So in this case, it's easy to see that 3 times e to the x is 3 times e to the x, and 2 times the derivative of e to the x is 2 times e to the x, and the second derivative is e to the x, so e to the x plus 2, e to the x, 3 e to the x's. So this is an easy one. There are more solutions. And like with numbers, differential equations can have no solutions, some solutions, infinitely many solutions. And each of the solutions is a function, which in itself can also have some solutions or infinitely many. Now, one problem with differential equations, they're a bloody mess. Like, there is no general and effective method for solving differential equations. You have different techniques, methods, tricks that work for different types of differential equations. Most differential equations are unsolvable. They're impossible to solve exactly, and you have to use approximations. So now the obvious question to ask would be, okay, so yeah, this is a weird mathematical structure. What the hell? What's the point of this? Well, the point of it is that, paraphrasing Galileo's famous quote, the book of nature is written in differential equations. It's not just written in mathematics. Nature is basically, or our understanding of nature, to be more precise, is basically differential equation models in physics and in biology and in chemistry and in other things. Yeah, all the great laws of physics, gravity, heat, liquid flows, etc., they are all differential equations. So, what physicists do, among other things, is basically work with differential equations. And finally, now that we know what differential equations are, it's a very small step to partial differential equations, and we conclude. So, if you remember, when we talked about algebraic equations, we said that if there is one unknown, it's easier to solve, it's easier to deal with than if there are more than one unknowns. And the same thing happens with differential equations. If they have only one unknown, they're called ordinary differential equations, in which case there's only one unknown function or its derivatives. And there are partial differential equations where there are more than one function or its derivatives to take into account. And typical examples, the one you have on the right, the Navier-Stokes equations, very famous ones. The first image is representing the diffusion of heat. The heat equation is also a very famous partial differential equation. Now, if OEDs, that's ordinary differential equations, are hard as hell, now PDEs are it's another dimension of difficulty. They're a bloody nightmare. But so why? What's the point with them as well? Well, the same point as with differential equations in general. Problem is, most of the differential equations that are used for mapping nature, for modeling the laws of nature, are actually partial differential equations. They're the hard ones, because for most processes that you can think of in nature, you have more than one thing that is changing with respect to time at the same time, which means you need different derivatives, which, as we said before, are basically rates of change of things with respect to other things. So they're a nightmare, but if you want to do any physics, you basically need to work with partial differential equations. You have to take into account more than one variable. And this is it. I hope it was clear enough.